So you're recording. Okay, that's brilliant. So I don't know whether you want to introduce yourself, Mike, while people are still jumping on.
Okay, I'm Mike Allen. I'm in Pencord in Martin's team at the University of Exeter. And I mean, my interests are in simulation, modelling, data science. I spend most of my time probably now working in stroke, where we're using both pathway simulation and machine learning to mimic the stroke pathway. We're using machine learning to learn decisions that doctors make and ask questions like what treatment would they have received if the same patient had gone to another hospital. And that's actually where this work started, in that we're using a lot of confidential patient level data and we can't publish it. And so we want to be able to publish something that people can use to understand the model. But now I'm getting onto the presentation, so I'll stop there. That enough, Martin?
Yeah, I think that'd be fine for now, Mike. I'm just still are a few people coming in, so I think 5 minutes is the standard amount of time that people leave for this. You're not showing full screen yet, Mike. I don't know if you knew that. You got to. So I suggest, yeah, you kick us off. And as I said earlier, for those that may not have been here at that point, Mike's going to talk for about half an hour and step us through some of the elements of synthetic data, and hopefully generate a lot of interesting questions. If you want to ask questions during the presentation, then put them in chat, and I'll, if necessary, I'll interrupt Mike if there's points of clarification that are needed. Otherwise, we've got lots of time at the end of the presentation for sharing discussion and asking questions and so on. So, Mike, you can start. It's 5 past.
Some work that we've been doing on synthetic data. I know we've got some M.Sc students here, hopefully listening in. I'll end the presentation, so you have to listen to all of it, with, I think, what will be quite a fun project, which is one of the projects that will be available on the M.Scs around this. So hang around for that. Okay, so this is what are our first trials, our experience, thoughts so far. And it's far from a complete exposition on synthetic patient level data. It's more run through some techniques we've been looking at, where we might be going, and then hopefully we can decide on, you know, if there are more people interested in this, working together. So it's all fake. Everything I'm talking about isn't real. And that's always worth reminding ourselves, that no matter how close our synthetic data may appear to real data, it is ultimately fake. It belongs to a different population than our real data. The two will never be identical populations because, well, one is real and one isn't. And so we might steal a quote and amend it a bit and say all synthetic data is wrong, but some of it is useful. And I'll apologise to those who are aggrieved with me saying data is. But that's common English, and I'm an advocate of open science, which advocates for plain English in communicating. So, but please replace that with data are in your brain if you like to. So yeah, it's all wrong, it's all fake, it's all belongs to a different population of data, but hopefully it's going to be useful, and we'll see what some of the uses are. I hope I'm not saying anything too controversial here. I will also admit there is absolutely nothing new here whatsoever. In fact, I don't mind saying I'm 54 and I've worked out I've never had an original idea in my life, but I'm reasonably adept at stealing ideas from other people and seeing how we might use them. So what I'm doing here is just trying to borrow from other fields and see what we might apply to us. So nothing new, and perhaps we ought to start with tipping our hat to what is probably one of the nicest collections of synthetic data around, the Simulacrum, which is synthetic cancer patient data that's made available. And the process that they used appears to be a very loving, almost handcrafted, bespoke process based on a directed probabilistic graph where you sample each feature at a time, depending on the route, and the distribution you use depends on the route that you took to get there. And it's a very nice piece of work. Their health warning, I think, is very applicable to everything we're doing. It's synthetic. You don't use it to make clinical decisions. But because it's the same structure, and that's an important point we'll come back to, same structure as the real data, you can use it to plan and refine analysis and test your methods before making a formal request for the official data. And so everything you develop on the synthetic simulacrum data should then work on the real data. So it saves you a lot of time and struggle before, by the time you get to the real data, you've got something that's kind of, the methods should be 90% there. So that's, they're sort of saying what the data is used for there. And I think that's something that is kind of obvious, or is obvious, but we've learned is that, well, what's fit for purpose synthetic data? And it all depends really on what the purpose is. So some example purposes I've put here, and the first one I've bolded, not that you can tell it's very bold, but it's where we're coming from. It's what drove this. We're doing this because we needed to do it. And we needed to do it to illustrate a model, a stroke pathway model that uses patient level data in a machine learning model. And we want to be able to share that model so people can understand it, test it, tell us it's wrong if they want to, adapt it, improve it, whatever. And to do that, you can't just put a model out there, the code, without any data for it to work on, because there are very few people who can look through code and say that's right or wrong without actually being able to run it and test it and poke it and prod it. So we wanted some data to go with it, and that data can't be the original data. So we want to have synthetic data that is good enough for that purpose to share the model. Other times it might be used, we might want to use it for teaching purposes or for student projects, for them to understand and explore an area. It could be that they work on a real problem with NHS data as its source, but by the time it gets to the student, we've produced a synthetic copy of that data that they can work on for a project. It's used a lot already, particularly in credit card fraud, which thankfully apparently is very rare, really, compared to the number of times credit cards are used non-fraudulently, to augment data set, particularly when you've got minority class data. So very few fraudulent credit card uses. And if you're training a machine to detect fraudulent from non-fraudulent, it's used, and we'll look at the method they use, because we'll steal from it to use it to make synthetic data. They use it to augment the current data, so it's used in that case. To train a model more efficiently, I think this is lovely work that's emerging, especially from Uber, on producing synthetic data sets where the individual cases in the data, you can represent the whole population variance in a smaller data set, maybe 10 times smaller, or even more compressed, by creating synthetic data which is picked and refined and shaped by its ability to train a machine with fewer examples than the source data. So that's lovely work that's kind of emerging. To be able to share data publicly to allow method development. So, as data scientists, I think a lot of us will have a look what's on Kaggle if we want to start playing with something. And to be able to produce more NHS-like data sets, I think get them out there for all the departments who don't have good links with the NHS to start chewing on more. I think that would be good. As with the simulacrum, we're talking with the National Stroke Audit about what we're doing. One of the things they'd like to do is to be able to make stroke audit data, a synthetic data set available to other people that they can share. And then at the bottom, I've got to completely replace real data, and you'll notice hopefully I put a cross by that, because we're not trying to do that. What we're trying to do is these other things which we think are useful. So first question, or we can sort of say, what do we mean by fit for purpose again? And there are two things that I've learned through doing this. One of them is, does the individual synthetic patient data resemble real patient data? So on the top here, we've got a face, and we can ask, well, does that look like a real face or a fake face? And that's one thing, you know, does it pass a Turing test, if you like, of saying, do you think this is real or not? And then the second one is the population of synthetic patient data fully representative of the real population? And that's slightly different, because here we can say these are male faces, but are they representative of the population of male faces? And you might argue not, because these all appear to be perhaps in their 20s. Nobody appears to be wearing glasses. I think they're all probably, or nearly all, pretty good looking people. This actually isn't synthetic data. This is just what happens if you type in male faces into Google. You get we all look like that, apparently. So we need to ask about the population as well as the individuals. So our aim is, we're looking for very general purpose methods, open methods. We want open code running on open software that everybody can replicate and change and adapt and share. That is very, the general purpose. Simulacrum used a very bespoke method. We're looking for things, theirs was kind of like the synthetic data that Harrods would sell you, if you like, where we're probably looking more at this is synthetic data that Tesco would sell you. We want to be able to produce it massively at scale, easily across a broad range of medical instances. We're using structured data, and we're using tabular data, and that may be simple, or it may be a more complex structure. We may also want to simulate free text data, or images, which I'll come back to at the very end. I'm just getting some messages from Microsoft Teams, so can I just check, Martin, am I still coming through?
Yeah, it seems fine from where I'm sitting, Mike. Okay. We've just had a couple
from my side.
Couple of funny chats that you probably don't need to look at.
Oh, right, okay. Now let me go back in. Sorry about that. Okay, now what we're also learning is, well, the quality of the synthetic data you need is different depending on what you're trying to do with it. But there are some general desirable characteristics, we might say. The data should have the same structure and data types as the original data, so that if you develop the method on the synthetic data, it will work straight away, bang, with the raw data going in. It should include all the categorical codes that may be encountered in real data, so you don't develop something on the synthetic data and then it falls over and says, I don't recognize that that it's encountered in the real data. And generally we want to see preservations of means, standard deviations, distribution shapes if we can, covariances, you know, how the different features, variables in the data are linked. Code that runs on synthetic data should run on real data, and also results from the use of synthetic data, you know, they may not be perfect every time, but they should, we hope, should be generally indicative of results from real data. So I'm going to go through pretty quickly some different things we've been looking at. The methods will go from ones that are pretty simple, easy to implement, reliable, explainable, computational, cheap, or run on a laptop, but can soon hit limits. Whereas we're going to then look at the new emerging techniques, the sky's the limit, but they're complex, they can be unstable, they can be unfathomable at times of how they've produced it. They're harder to implement, but normally somebody has done most of the work for you. They can be computationally expensive. They can, need big desktop workstations with GPUs at least. I think they're also rather exciting, and by the time you go through some of the methods, you'll never trust anything you see again in your life. So the methods we'll look at is one based on principal component analysis. Next one, SMOTE, synthetic minority oversampling technique. GANS, generative adversarial networks, VAEs, variational autoencoders, and then I'll mention, well, I have mentioned Simulacrum, and we'll mention generative teaching networks, and just end with something slightly different, differential privacy. We've been mostly looking at two data sets to test this. One's very public, Wisconsin breast cancer data set, a lot of people know about, all continuous variables, and then you class something as malign or benign. And then we also have stroke thrombolysis pathway, which is a health pathway data set that is publicly available now, and it's mostly categorical or integer data. And the classes are whether that patient was given thrombolysis or not. We've assessed it to begin with, and these are things we're going to want to develop more assessment methods by comparing means and standard deviations between the original and synthetic, and also comparison of covariance between the features. Does the synthetic data maintain all the links between statistical links between features? And then what's really important to us is the practical side. Will the synthetic data be able to train a classification model? And here we've just used logistic regression. So we train it on synthetic data. Will that work on the real data then, that classification engine? So PCA, let's mention that. So I'm not going to go into all the ins and outs of PCA. A lot of you will know it already. Redimensions data along different axes. So on the left here, we've got this great slew of data. The first principal component, which captures the maximum amount of variance of the data, is this line along here. So that's one principal component. And then the second one will be orthogonal to that, which captures variance in this direction. So if we transform this data using one principal component, everything would effectively collapse onto this line here. We could take a mean and standard deviation from that. We could sample from our new mean and standard deviation population, and then transform it back into the real world, and we'd end up with synthetic data points which would sit along this red line here. And then we can repeat that. Instead of just using a single dimension, we can use two dimensions here. We take the mean and standard deviation of this axis as well, and we sample from that population as well. So now we've got two dimensions which have transformed those sample points back into the real world, and hopefully we get something that looks a bit like this scatter diagram here. So here's the results. I'll talk a bit more about this one and then fly over some of the others and just point out what's different. On the left, we have a comparison of means between and we're looking at our negative samples, so in this case, no cancer, and positive samples, cancer, the original data and the synthetic data. And you can see that they all line up nicely on a sort of one-to-one. So our synthetic data is representing our feature means. There are 30 different features here. They're all continuous variables. And similarly at the bottom, we look at comparing standard deviations of the data as well. So on our non-cancerous on the left and cancerous on the right, and we're seeing a good alignment of the data there. So converting to principal components, taking the mean standard deviations, sampling from those, and converting back maintains means and standard deviations. Also nice to see here, this is the pairwise covariance between features. So there are 30 features. So if we took feature 1 and 2, for example, and ran a correlation between those in the original data set, we might come up with an R squared, I don't know, of 0.6. And then, so this would be in the original data set, feature 1 and 2, correlation 0.6. And we then plot what is it in our synthetic data. And we can see that the PCA maintains the covariance very nicely. Different colours are 5 different repeat synthetic runs. We then test our model, and our original classification model had an accuracy of 97.5%, and our PCA model 96.7%. So our model is just as good, and our data looks good. So for this data set, PCA looks very nice indeed. With our stroke data set, we've got a different type of data set. We've got binaries, integers, and categories. So we deal with binaries and integers. The raw data synthetic output is continuous in the methods described here. So we simply round to an integer. And if it's a binary, we clip the output to 0 or 1. So if after we've rounded it to an integer, it comes out at 2, we clip it back to 1. We may consider clipping for other integer ranges as well. We haven't actually used it here. For categorical data, we encode it as one hot, some of you will be familiar with. So if we've got a category hospital, it's hospital number 2. We categorize all the hospitals as binaries, 0 or 1, and our one hospital 2 becomes a 1. So 1 is hot out of 4. And hospital 3 gets coded as a 1. Our synthetic raw data, synthetic data that comes out and the model is again continuous, what we simply look for is the argmax, which is the index with the highest value. So in this case, it's hospital 2 is the highest, so we classify as hospital 2. Here it's hospital 3 is the highest in the raw output from the synthetic data, and we classify as hospital as 3. So same sort of graphs again. We noticed things aren't quite so nice, but they're pretty darn good, really. But we're getting in the synthetic data, some of our samples are having, some of our features are having lower means than the original data, and this particularly appears with those that are very low values. So they're probably, I haven't actually looked in this case, they're probably ones that are binary, where only a few of the original data points are 1, and we're losing some of the frequencies of those in the synthetic data. So not quite as good, but not bad. Same with the standard deviations. Synthetic data standard deviations tending to be lower for the lowest values. These are log scales in case you hadn't noticed. Our covariance isn't bad again, though we're starting to see more scatter around the place here, so not quite as tight as with our very simple data set. Our accuracy is originally 81.5% on this, so this is a different classification model, and our PCA 80%. So not bad. Okay, SMOTE. Synthetic minority oversampling technique basically looks for near neighbours of data points in the same class. So if we've got these data points that are green, we pick one of them at random. We then pick typically between 3 and 6 nearest neighbour points to them. We pick one of those at random again. So in this case, it's going to pick this one that's turned yellow on the left here, and then we generate a new point at random between these 2 existing points. The one it illustrates is sort of bang in the center, but the actual method will choose a random point in between. So normally this is done to augment the original data set. What we then do is remove all of the original data points, and we're left just with these points that have been generated as being somewhere between 2 near neighbours. This is in 2 dimensions, absolutely no reason why you can't do it in 30, 50 or 100 dimensions, which we've done. Just don't try to visualise it because it hurts the brain. I'm now just going to stick with the stroke pathway because it's the harder one to model we saw. So the paper that I'll link to at the end, that has the Wisconsin data set for everything, but the stroke data set is harder. if we look here, the SMOTE, again, we've got some reduction in the means, again, of the lower values. So we've got the same sort of problem, maybe not quite as bad, though it will perhaps similar. And again, we've got the overall covariances seem to be pretty well maintained, except we start to get a bit of scatter towards some of these at one end. The accuracy, original 81.5%, and our model trained on synthetic data and tested on the real data is actually outperforms PCA, and actually outperforms the original, appears to. That may or may not be. This is the standard errors. Haven't done a statistical test on this. It's going to be close to significance, but SMOTE balances out data classes, so you get an equal number of positive and negative classes. So we might expect it to help improve. I don't know. It's good though. The training is good. Okay, so on to some more exciting and adventurous methods. These sites are fun to look at. This person does not exist on the left. That person does not exist. And a site I've just come across, this cat does not exist on the right, and that is a picture of a cat that doesn't exist. And these were imagined by neural networks trained to produce synthetic faces or synthetic cats. So we start to see now the complexity of the data that can be synthesized is starting to get really quite interesting, more than just tabular data. For those nerds out you who use Stack Overflow, there's a site called Stack Overflow, and that uses a generative network to produce fake Stack Overflow questions and answers. Brilliant. It's just so nerdy. But it shows the serious part. It shows the growing ability to synthesize multiple component data. Other things that don't exist for your delight and delectation. That's a piece of artwork that doesn't exist, comes from a network trained on what a real art looks like. This is brilliant. This MP does not exist. It's trained on all the MP photos. Have a look at that. They all maintain this smarmy grin that MPs all seem to have. It's marvellous. And this chair does not exist. And the serious side of this chair does not exist is that these things can start to be used by creative designers to give them ideas. You can try different things. You can sort of say, I want my chair to be more weird or less weird. And so we're starting to get synthetic design here coming in. GPT-3, you might have seen in the news. I mean, this is getting really quite scary now. It's the most powerful neural network ever produced. By a long way. Before, the most powerful was GPT-2, and this one's much bigger. And it's learned by basically consuming the internet. It can generate tweets, stories in any style. It can generate recipes. It can produce Excel functions. And there's an article here from The Guardian that it was given assignment to write an essay to convince people robots come in peace. And you can see, I'm not a human, I am a robot, a thinking robot. And it's a very convincing article, and it can do things in styles. Worth looking more into GPT-3. It's both amazing and scary. In this case, you can tell it's a fake. It's The Guardian, and there are no spelling mistakes in the article, so can't be real. Right, this one's worth looking at, using a generative network to transfer motion. Put the YouTube link there, won't try and show it now. Transfers the dance of a professional ballet dancer, detects the pose, and transfers it to a person who is sort of vaguely trying to do the dance but can't get anywhere close. And I think what's exciting about this, apart from its fun and its video, it's the potential to transfer characteristics from one place and superimpose on another. So we could potentially generate more disease-like patient records than there are by transferring characteristics of a disease somehow onto a healthy individual patient record. So how do these things work? And we'll have a look at our first use of it. generative adversarial networks have two networks. One is a discriminator that's job is to say whether data that it sees is real or is fake. And this is the only one that sees real data. There are two networks here, the discriminator does. And it's shown fake and real data, and it's told whether it then gets feedback. Were you right or wrong? Did you detect whether the fake data was fake? And so it improves by getting that feedback. That, though, is the feedback into a generator network that has to generate images of cats or dogs or whatever. And its feedback is, has it fooled the discriminator? And it adjusts itself to try and fool the discriminator. So you've got this war going on between the generator and the discriminator. They're each getting better and better. Only the discriminator can see the genuine data. And you know, this is what's producing the fake images. It's just a beautiful idea. Ian Goodfellow's the chap behind it. He's got quite a few YouTube videos on it. He's really good speaker as well, worth looking out for. So when we look at it, means, standard deviations, a bit messy, but basically maintained. Covariance, a bit of a splurge, but basically pretty well maintained. What's disappointing, though, for some reason which don't understand yet, is the training of the network is poorer. We've only got 68% compared to 82%. So something's going wrong, which we need to sort of dig into more here. Variational autoencoders. I'm going to, for the sake of time, I'm going to skip over this because I think these probably will be disappearing as GANs take over the world. But again, we get reasonable data. Summary of our machine learning results with our Wisconsin data set. This is the continuous data set. They all perform pretty well, though PCA and SMOTE are best. So they all work well on that reasonably simple continuous variable. On our one that's chocked full with categorical variables, PCA and SMOTE were better. At the moment, GAN is not so quite good. And what's disappointing, CT-GAN is a tabular GAN, conditional tabular GAN from MIT, specifically for it worked very well. It's utterly lost all the covariance in the data. And there's nothing you can do to tweak it, so I'm pretty sure it's not me that's doing anything wrong, because it comes basically as you just feed it the data and it feeds out the synthetic data. So our current and our planned work, more on GANs, because these are the things that are really advancing quickly everywhere. Looks like the kind of future of complex synthetic data. We're looking to optimize the parameters. So those of you familiar with neural networks, the common stuff. How many layers do we use? What optimizer do we use? What activation functions do we use? And then there are various modifications that you can build in different class labels. We actually train separately all the negative class and all the positive class. Conditional GANs deal with them both at the same time, or as many as you want. And stability GANs, you can find that the data they're producing gets better and better at training the machine, and then it just goes crazy. The network just kind of loses all sense, if you like, and the performance plummets. Wasserstein GAN is trying to improve stability. Style GAN, again, it's another different classes. MedGAN, there is already one for synthetic patient data, but it's all around code generation, so list of ICD-10s, for any of you those familiar with that. So it's not very general purpose. Generative teaching networks look really nice to look at, which we're going to start looking at. So these are the things that they optimize the data they produced based on the feedback of how well that data trained a machine learning model. And this is the work that Uber in particular are coming out with. There's a variation on SMOTE we've used before, which deals with categorical data another way. bringing data from multiple methods, maybe that's good, rather than saying, well, let's have all data from GANS, all data from SMOTE or whatever. We're going to look at more data sets. We want to look at more assessment tests, and also want to look, which I've got 2 slides just on things I haven't really mentioned much. I'll talk about that in a second. So generative training networks, this is just here for your reference in the slide set. There's a blog from Uber, what they're trying to do, and a paper. And it's about producing condensed data sets that can train machine learning models much more efficiently than the original data, or certainly with much fewer examples, which allows you to try a lot more different structures of neural networks and such like. So more experimentation. And then differential privacy is something a bit different. Some of you may be already familiar with it. It's what people like Google use to obfuscate data they collect about us. They use it internally, and it allows you to add random noise to data, and you can adjust how much you obfuscate the data. And IBM have produced a nice Python library to do it. You can just pip install it here, and there's a blog and a GitHub page and how to install it here. So I think it's going to be really exciting. This was the progress on GANS over a 3 to 4 year period on face generation. So, you know, this stuff is developing very, very quickly in its sophistication, which I think makes it really exciting. There's a paper that we published in medRxiv, which describes our early work. And all the data used and all the code to produce everything we've done is on in a GitHub site, so the link there. And then just finally, for those with who are doing the M.Sc, there'll be a project announced amongst the many projects you might choose, where want to look at the ability of GANs, or generative teaching networks, to synthesize brain scan images that can train a deep neural network to distinguish brains with cancer from those without. That will be based on a public data set from Kaggle, and we'll look to see whether we can produce synthetic data, and with generative teaching networks, whether it can actually improve the performance of the training network, or at least the speed to get to the same performance. Okay, that was a bit of a whistle stop tour. But you know, I'll send out the slides. There's the paper. So
thanks, Mike.
Okay.
Before we get into questions, I was just going to ask you, I mean, obviously some of us will be very new to this whole field of synthetic data. Very interested in finding, for beginners like myself, recommend as a sort of synthetic data beginner's guide, or synthetic data for dummies type approach. Other particular sources that how did you learn about it, for example? What brought you into it and got you?
I learned about it in my usual way, which is stumbling around in the dark, bumping into things, getting leads and finding out about other stuff, seeing what other people were, you know, doing. Once you get a few leads, you can start to see. I don't know. I mean, one of the problems, or not problem, one of the things is people are producing this stuff for different reasons. So, you know, the motivation behind GPT-3 or GANS is very different to our motivation, even though the methods are useful to us. So I don't think there is a dummy's guide to synthetic data, but if there is one, perhaps somebody else knows of some good
maybe sources. Some of people in this audience are a bit more informed, know of good source material for people wanting to sort of pick it up and learn more. Before we turn to sort of asking questions with hands up and so on, Eudis, you put a question in the chat which we must cover. And Eudis's question was: the testing set for the SMOTE and PCA consisting of real data? So I think that raises questions about, you know, real data to generate synthetic data. And
yes. Well, for the sort of thing that what we're doing, you always need real data, because we're basing our synthetic data on learning from real data. So we need the real data, and then we test the models I described. They were trained on synthetic data and then tested against real data. So you need it for that as well. I mean, do you always need to have real data to produce synthetic data? I think, well, you know, we're modelers in Pencord, so we'd say absolutely not to that. We spend most of our life generating synthetic, you know, time from ambulance to arrival at hospital time sampled from what we produce. What we're trying to do is data released that mimics a real data set. We always need access to that real data set.
Okay. So I'll open it out now. If you want to ask a question, please put your hand up and I'll invite you to come on screen. And it's nice if you can turn your video on.
Yeah, how do I, let me stop sharing if I can find that.
So see if anybody's got some tips about where to learn more. So Eudis, you've got your hand up.
Hello.
Hi, Eudis.
Hi everyone. Thanks, Mike, for that talk. I just have a question regarding the governing of synthetical data, because it seems like it's quite susceptible to researchers' bias to be able to make their own imaginary data in a way.
Yeah, and that's one of, you know, that I think that's an important question of, well, how do you say this is shareable or not shareable? And I think to begin with, I was expecting to find some clear guidelines or rules naively, and there aren't any of those. So for us, for example, we want to release a specific synthetic data set. We want to release data that's produced, that's based on national stroke audits data. That raw data is controlled by HQIP, who are the sort of governors of the national audits. And so for us, it's a case of we need to do what it takes to persuade them to allow us to release it. So they are the custodians of the original data. They are the ones that will say to us, I mean, in theory, we could say, well, we don't need to, but I think that would be a really stupid direction to go in, because we want to work with them, and they're interested. So yeah, it's a case of what do the original people with the data, what will they accept as that they're not going to get into trouble?
Yeah, it's an interesting one, isn't it? You know, because to some extent they have provided you with the data that is used as a basis for the synthetic data. So ownership of the synthetic data is
yes, who owns
an interesting ethical issue there. Anyway, I'm going to invite Simon, who's from the school of this is not a real politician, who's got a question.
Absolutely. So how do you know you're not synthesizing duff data, I guess, and how do you know? Because obviously, I guess if your base data is a bit duff, then you're just going to make another duff copy of it in some way. And how do you know you get a big enough sample size for it to be relevant?
Yeah, by duff, do you mean things like there's mistakes in data recording and things like that?
Yeah, or just skewed in some way, I guess, if you haven't
got
enough sample. Or...
So the original data set that they give you is not representative of the full population.
Yeah.
In that case, the synthetic data, and it's the same with all machine learning really, it learns on what it's given. So it will replicate bias and duffness of the original data set that you have. So but you've got the same problem there in, I mean, hopefully with all these things, we then test, we should always test our models on certainly machine learning data that have never been used for the training purposes. So you'd perhaps, if you have worries about your test data set that you've been given, you build it and then you ask for some separate data to sort of see how well it works on that. But we'd always set aside some data right at the start it will be tested on later. But I mean, machines learn the biases of, and it's scientists who pick what data to use. And it's very frustrating because we can go to HQuip and say, look, you're asking us to justify all the fields we want. That means we bring our biases to you of what we think is useful and not. We'd actually rather build our models without bringing our biases and let the data tell us what fields are useful or not. But, good luck with anybody who goes to HQuip with that argument. It's not going to go anywhere.
Okay. Yeah, lots in that question too. Chris, you got a question? Chris McWilliams.
Hello. Sorry, trying to unmute myself. Thanks very much, Michael. That was a really, interesting introduction. And I wondered if that we would like to synthesize is very much like multivariable time series data, either from the intensive care unit or from electronic ward observations in hospitals. And I wondered if you know of any methods that are specific for that, for generating that kind of data.
So I think that my best, it'd be lovely to try that sort of stuff, would be a convolutional neural network, because they deal with time series, and there's no I'm pretty sure there are generative networks already with convolutional components in them. So yeah, I think I'd use, or ones with memory, actually perhaps would be better. LSTM, long short-term memory networks. The neural network should be able to deal with that perfectly fine. There might be more simpler statistical methods.
Mike, so did you have a follow on for that, Chris?
No, I've got a potential different question, but that's fine.
Yeah, just one thing that occurs to me, Mike, you obviously didn't have much time in this webinar to talk about the actual sort of technical method you used to generate your synthetic data sets, and I'm assuming most of it's been done with Python based programming. Maybe that's a wrong assumption, I don't know, but
is there another programming language?
Yeah, I think so. From memory, there's a few more, but I'm putting you on the spot. I mean, would it be possible at some point to introduce some of those sort of programming methods, or to offer it as a workshop at some point?
Yes, I mean,
could that easily be done? I mean, what would be required for doing that? Because I detect there might be a lot of people here in this audience who'd be interested to learn more about the actual methods you used and how to do the programming and so on.
Yeah, so I mean, we can offer yes. I see no reason we can do a workshop on that. I'm just sort of checking the GitHub page with it on. I'm pretty sure you can run the code online with that. If not, I will put that on. But I thought I'd put that on. And then so you can see the code running.
Is that GitHub accessible by everybody here? Is it?
Yes, it is. Yeah. Oh no, it doesn't run online. I remember the reason now. They each require different Python environments to be set up, so you can't do one thing that will run them all. But I mean, it describes how to set up the environments. People can contact me for more information. But yeah, all the code is there. It's all into Python notebooks, which explain, each one's got an explanation of what the code is doing. And, with diagrams and such, more than I've gone through before. And then all the code, and the code is hopefully reasonably well commented and described throughout. It's there as examples to work through.
So could we kind of pin you down to doing another one of these, looking at more of the technical issues? So I'm going to get you to say it publicly now, so we can. But I mean, sometime next year, maybe we could have a mini session on the actual technicalities of using SMOTE and some of the other methods that you mentioned.
Yeah, we'd probably want to pick one and work our way through that. I mean, it would be just a bit too tedious, I think, to go through more than one technique in one time. But for those reasonably familiar with Python, maybe so the GANS, you need a basic knowledge of neural networks for and how to build. But yeah, probably a sort of 3 hour stint would be more. Actually,
Yeah.
that would be more than enough.
Martin, can I just chip in with a suggestion? So I would agree with Mike, and perhaps as prep for that, I mean, just to say that the HSMA program videos, the lectures that don't cover synthetic data, but build on a lot of the methods that synthetic data will use and will get you to that point. All of that stuff's going up on YouTube, so and is already going up on YouTube. So that might be a way that people can get sort of a bit of background before Mike does that session to sort of get them up to speed on the kinds of things that Mike would then talk about.
Sure, for sure. Yeah, I think we got plenty of time. But I was thinking also the data science M.Sc students might be very interested in an optional session, for example, on generation of synthetic data. But we can talk about that, and I don't think we can do it before the beginning of next year. But maybe that's something we can look to in time. Chris, you've got your hand up. Is that a legacy hand, or did you want to ask another question?
I'll ask another question. Thanks. It was actually a legacy hand, but I was so I think slightly related to Simon's question, but use cases for synthetic data and like particularly GANs that I've heard thrown around is for classification problems where you've got imbalanced class sizes to generate, and you mentioned it in your talk, to generate more instances of the negative class. But if you haven't got many instances of the negative class in the first case, does that really work? It's not something I've really looked into, but is that not limited by the small class size in the first place?
Yeah, I mean, potentially that if it hasn't got that many to learn from. And to be at the moment, I don't know how many. I mean, these aren't big data sets we're using here. They're the histology one, the cancer one's a couple of 100 rows or something. So they're not massive. If you haven't got much and you're looking to try and create some variation, it could be variational autoencoders, maybe the better way to go, because built into them is this idea that they go through a layer that forces a distribution of data into you can think of them as very simple, say similar to principal components, and you could change the variation in that layer and to try and produce more wide-ranging examples. I think the question then would be, well, are you introducing a useful extra amount of variation to explore things, or are you producing something that's not useful? And I guess only testing will produce that. But yeah, it could be in that use case, variational autoencoders may be better.
Okay, I'm going to be a bit cheeky and ask Simon, do you want to go first, or shall I go first?
You can go first. That's fine.
Yeah, I was going to be a bit cheeky and invite, because I know Rob Challen is with us. I hope you're still listening, Rob. You've done a lot of work looking at issues to do with de-identification of existing clinical data sets. And I wondered if you've got something to say about the distinction between using a method of de-identification versus using synthetic data. To some extent, they strike me as being obvious alternatives in some situations that you might want to.
Yeah, okay. So I suppose de-identification of data has kind of been used for a long time to try and produce data sets that can be used more generally. It has quite serious limitations. Data, a lot of data sets are maybe really specific to the person and as a result can be used as proxy identifiers. So even if you strip out all the names and dates of birth and everything, even if you can find out that, for example, a woman has had 2 children on specific days, that those 2 birth dates are enough to be able to uniquely identify 50% of the women in the UK. So it's quite a challenge to actually de-identify things when faced with a kind of motivated attacker. with significant amounts of data at their disposal to which to sort of force re-identification. So obviously, having a completely synthetic data set is quite helpful in those situations. I suppose you know, the alternative to that is to protect the data set to a certain extent, and look at where you can use the data set. So in many of this kind of clinical research environments, there are quite strong constraints about who can access them and how easy it is to get data in and out of them, and that's a kind of alternative approach.
Rob, sorry to butt in, but why would you not use synthetic data?
Well, I suppose the question is whether the synthetic data accurately models all of the interdependencies when you may have very small numbers of people, you know, that are in a particular edge case. So, you know, you might find that, for example, that particular for 50, those that are over 50 with a particular genetic makeup, with a particular you know, so there's quite a small group that a medication does or doesn't work for, and whether a synthetic data set will ever recreate that small group in a way that's meaningful or can be connected back to reality is a big question. So I think, you know, ultimately it is going to lose information because you can't create information in that way. The synthetic data set is going to have a higher entropy than the original data set, and there will be some edge cases lost. So if your job is looking for edge cases, then it may be less good.
And it might be a particular problem with small numbers from what you're telling me.
Yeah, although, you know, sooner or later, groups like that will become small numbers, even at the best of times.
Thanks. Simon, sorry, you had a question. I came in before you.
I can't remember now. I'm sure it's really very interesting and informative, but I've completely forgotten what it was. Sorry. It'll come back to me, I'm sure.
Anybody else got thoughts? It doesn't have to be a question. It might be people who know a little bit about this who want to add their. Udis, you got another point to make? Was that legacy?
No, I've got another question.
Yeah.
So about the M.Sc project, is the sort of ideal student that you're looking for? Was that, like you said, the Python person familiar with neural networks, or is there some sort of skill set that's not taught outside the master's degree potentially?
No, there's nothing not taught outside the master's degree. It'll be Python with neural nets, but the project, I think, would just require somebody with enough confidence in their Python skills that they can get to grips with a neural net framework. But these are all quite well described elsewhere as well, and it will either be in TensorFlow or PyTorch. I mean, it could be the student chooses which one. So I think somebody comfortable with getting into Python and neural nets in particular, which hopefully by the time, I think you cover some in this term. I mean, there used to be horrendous things to deal with, but they're not now, because you've got Keras sets with TensorFlow, which makes building them. Well, you'll be able to see in the code, you know, it's the actual neural net is both nets together, maybe 20, 30 lines of code, so not more than that. And then PyTorch is very nice to build as well. So these things are much easier than they were a few years ago.
So Chris, you've put a thing in chat with a web reference that may be useful to people. See that? Any other hands up? So I've got another question. If not, Mike, I mean, from what you've told us, this is a really sort of fairly recent and also a really fast-growing field of research, based on what you've showed us. I mean, just those pictures where you track through the changes since, was it 2014?
Yeah, 2014.
It just illustrates just how recent and how quickly moving this field is. How do you see things developing as this goes forward? Because I mean, is it a case where you can see many more methods and algorithms being developed over time? And it's hard to predict exactly where it's going to lead us.
So I think if I had a crystal ball that you asked me to stare into, then of course I'd probably almost certainly be wrong. But I think from what momentum is with GANS, and the momentum is with, well, neural networks generally, and being able to synthesize increasingly complex data. So, we talked, today about time series data, and then, the next step is, well, you've got correlations of time series data. And I think certainly in terms of research and application, and for us, because we're not going to want to get into the nuts and bolts of completely novel methods. It's looking at what else is coming out from often the big labs at Google, Uber, Facebook, MIT, and I think it's almost certainly generative adversarial networks for the foreseeable future, until something else comes along that's equally disruptive.
Yeah. Another thing I was going to invite, we've got a few people here who work directly as analysts and business intelligence type people in the health service. I was really interested to know, say, Lee, what your views are on how useful techniques like this can be for helping the health service directly. Because I mean, we tend to have presented this mostly in the context of research work, but in terms of direct relevance to the NHS and its analytical function, how do you feel this plays in? Or if anybody else, Catherine, did you want to say something? No comments on that.
Yeah, no, I will if it's sort of. Yeah, I think it's really interesting in terms of it's really the question that we have, or the problem that we have, I think that Michael alluded to, is opening up the access. We want more people to come in and support us looking at some very large and very complex data sets, but it's very hard to get it out there. And I think that, looking at the direction of travel on this, I think there is that mutual benefit in what you say. It's looking about building the models and bringing that something in that we can then finally deploy onto some of the data structure that we have. I think there's a lot of potential here, and I think it's very interesting. You certainly got me thinking about this. And I was just wondering if, so I think there's a benefit going forward. The question is, could we generate some synthetic data we hold and use that to sort of get more insight and more modelling on that? That's just my general thought.
Yeah, it gets over a lot of the information governance issues and sharing issues, doesn't it? I suppose is Lee, you were next, and then Simon.
Thanks. Yeah. I think sitting at the bottom, if you like, of the NHS tree when it comes to data, I think when we're sort of applying to NHS Digital for a new data set, it would be great to have some synthetic data in advance of that, where we can then sort of run some analyses against models, against everything just in advance of when we actually receive that data, because it can take years before we get it. So to have some of those, to have some of the analyses and models up and running, so that when the data finally gets in, half the work has been done already. That'd be invaluable, I think, to us.
So before we go to Simon, Catherine, did I cut you off before you finished? Sorry.
No, you didn't. It was just building on what Lee was saying. I think there are two other things on this. Yes, the speed at which you can get stuff done, I think, could really, really be improved. I think the second, the the other couple of points is the de-identification problem is absolutely right. Everywhere you go to, especially the more deeper you get into health data, and especially where we're looking at the sort of wider antecedents and that more population health based, it becomes harder and harder to get away from needing a level of personal information that negates the de-identification. So that would be helpful. And I think then the other thing that Michael raised about the bias, does this offer us an opportunity to say, well, we know this is what the health data that it looks like. We know this is what's in the pot. If we could synthesize what's in the pot without reference to, I'd like this field, this field, this field, and this field, you might have an opportunity to put a model on there that is you can test for those biases in the data that already exist. And I think that is also a potentially exciting field, because that's one of the things that's coming up very strongly at the moment.
I mean, certainly it sort of strips away all the incentives and all the worries about the confidentiality of individual patient data, doesn't it? If you've got, there's going to be no point in anybody trying to sort of hack into it to identify people who don't exist. Simon, you still got questions, I expect.
Yeah, no. I mean, I've just, again, building on what Lee and Catherine said, I mean, you know, we're really trying to get communities together around sort of sharing code and processes and models and, you know, analytical techniques. And it's really hard to, you know, I can write a really nice bit of R script that does some beautiful sort of thing. But if I want to share what I've done with another trust or whatever, you've then got to try to make an anonymous data set or put some dummy data in there. So to be able to have a synthetic data set that's just available and that, you know, is out there and open source and people can play with will be absolutely fantastic. And the ability to adapt that to your own little bits, if it's really quite simple to sort of chuck your data in and get some synthetic data out, sounds fabulous. Yeah,
I think that's one of the easier targets, Mr. President, because you're not in that case, and it's what we're using it for. You're not worried about whether it's got every fine detail or how fine detail is. It's something that's usable and reasonable with that model, that other people can check the model works, that they're using it right, and then can pop in their data. I think that's should be one of the lowest hanging fruits on our synthetic data tree that we can pluck.
Yeah,
that will be very bigly good.
Bigly good. Andrew, you got a question?
Yes. Hello. So the first thing, I got to apologise because I came in rather late, so I only saw the last couple of slides of Michael's presentation. But I wanted to bring something up, and hopefully you did, or maybe you did cover it. So it's what other people, you know, bits of other people say in terms of the uncertainty of the synthetic generation process. And are there any techniques that really deal with or present to you downstream the uncertainty in the synthetic data generation? Because from my thoughts, rather than perhaps giving out one synthetic data set, maybe one should give out many synthetic data sets, and which together will represent the uncertainty, and then you would do analyses similar to the kind of analyses you do in multiple imputation for missing.
I think that, Andrew, is a brilliant idea, and that you could. And what if we start to get to know the strengths and weaknesses of different data sets? We can say, look, here's a data set produced by SMOTE. Here's a data set produced by a GAN. Here's produced by variational autoencoders, or maybe certainly neural network land, which often seems to favour let's just max out the sort of computational expense of this thing. 10 different GANs, each producing a data set, and so each of one has learned differently, and so things that are in common amongst those sort of ensemble of GAN results you trust more, something you've only picked up from the output of one GAN you trust less. So I think that's an excellent approach.
They're still all going to be dependent on the source data, though, aren't they, Mike? So if there's any biases in your source data, they're going to get replicated in the synthetic data too. We can't get around that one. Yeah.
You can't unless you're aware of what biases you want to look for and eliminate. If there are biases that you know and you want to eliminate, there are ways now of trying to avoid them in neural networks. Brilliant.
Okay. Just to say, Andrew, we are recording this session, so it will be made available if you do want to go back and listen to the bits you missed. You've got a legacy hand up, by the way, there. Anybody else further thoughts or questions?
I think Tim's asked a question in the chat, Michael.
Oh,
I mean Martin, sorry.
Yeah, just to say, just to let everybody know where the recording will be going. That'd be great.
Yep, we can do that.
Just to add, just thinking in our crystal ball, as you presented with me with one earlier to look into, Martin, that, we're using tabular data at the moment. For the M.Sc student, I think that'll be the first time certainly we will look at brain image type data. But I know we've got sort of Rob Challen here and Dan as well are both excited by the what can be done with natural language processing and natural language, because doctors use that a lot as well. And so I think looking to the future, something fun and exciting we can do there, perhaps start with something simple. It's, can we start to synthesize the sort of natural text that you get in patient records as well? I think that'd be interesting.
Yeah, absolutely. But I was just thinking, actually, as you mentioned that earlier, especially about sort of augmenting data as well, because recent work that we did, one of the hospitals looking at patient survey data, I mean, great from because most of the survey data was actually overwhelmingly positive, but then you've got very few negative examples. So can we use synthetic data to try and augment some of the negative free text data to try and help with the learning? Because obviously it's a common challenge, and particularly in things like surveys, for most things, particularly anything in the health service, people are understandably biased towards, despite all the sort of general moans and stuff, people tend to say nice things because they've received care and people have looked after them, and generally have a sort of natural people respond to surveys. So there's something I think to be said in using synthetic data to try and bolster out some of the more negative things, so to be able to look for those things, and often the negative text that people write is of more interest to the trust, because they want to know what's gone wrong and what can they fix, and so actually picking up on those kind of things can be really important. So I can see a real use for it actually in that.
Yeah. Thanks, Dan. My thoughts are that very often the methods you use must be dependent on the objectives of what you're trying to achieve with a model and so on. But I also feel that there's I know if Gary is unable to join us for this session, he's a statistician at the med school, and he'd have a lot to say about understanding the limitations of synthetic data as well. So I think we need to be aware of how far we can push this tool. And also, aware of just how much the synthetic data will mirror or replicate any of the biases in the actual data that we use. I don't know, Mike, have you got anything to say about limitations of synthetic data? I mean, you said at the beginning you should never use synthetic data for clinical decision making, for example. So, do you have thoughts?
I think it depends what you're using it for. So, I think Rob highlighted. Probably what will be the most glaring one is, well, how many of the edge cases are going to turn up on that? So that comes back. I guess I'm sorry I forgot his name. He mentioned multiple data sets. Maybe the edge cases might, if we're training an ensemble of generative networks, which I've stolen that idea and will immediately set forth tonight on doing that.
That was Andrew.
That it could be the edge cases turn up in one, so the principle of a neural network. Let's get back to why are these things so popular and fun? is that if it is there to be learned, a neural network should be able to learn it. Now that's a big should, and the research is going on, but there's no limit to what neural networks can learn. So original data set, a neural network should be able to learn it if we set it up right and we make it big enough and control it properly. And so even the edge cases, that it could be that at the moment they turn up in 1 out of 10 generative network data sets, but you know, that could be interesting to look for what you learn from one data set and not from the others, because that probably tells you about the frequency of which that event actually occurs in the original data set as well. So, but yeah, they are limitations. We must never forget these are fake data. This is fake data. It's not real, and we must never kid ourselves that it is real. But there are various ways, if we remember that, various things we can do. We're trying to get as much out of it as we can.
Thanks. Any further thoughts? We've got another few minutes, but if nobody's got any further thoughts, we can bring this to a close at this point. Anybody further contributions? Obviously, there will be other things going on in relation to development in synthetic data. We'll make sure the recording, the link to the recording of this session is made available so that people can pass it on to those that weren't able to come. And we'll also keep you informed, everybody informed about the further web as coming. And I hope you found that interesting. And we look forward to seeing you at future events. Thanks very much. And thanks especially to Mike, obviously, for putting that in.
You're welcome.
Brilliant stuff. Thanks, Mike.
Thank you.
Thanks, Mike.
Thank you. Thanks, Mike.
Right. Bye-bye, everyone.
Thank you.
Bye-bye.
PDF.